This video is about doing the data analysis for experiment number 9, analysis of an acid-base titration curve, the Gran plot. So this calculation involves a bit of work, so go ahead and fire up Excel, sit back and get ready to dig in. So I assume that you have your data ready, and so it should look something like this that you downloaded. You'll have one of these for each titration, so we're just going to go through one of these. You'll need to repeat this for your second set of titration data. You might want to get somebody else in your lab team to help you out with this, but you can of course share the first spreadsheet that you made. Okay, so let's set up a few things to begin with, some things we'll need. So I like to set up some constants. So first off, we're going to need the molarity of the KHP solution. The volume of the KHP solution. And that'll be in milliliters. So that was 100 milliliters. Oh, by the way, this molarity of KHP, this was calculated without the buoyancy correction, assuming that you used 1.5 grams exactly. So your numbers may be different than this. That's perfectly okay, but it should probably be something near this. This data that I'm using doesn't necessarily correspond to that concentration. So my numbers that I get might be a little bit off compared to yours, but that's okay. It'll still give you an idea of how we do this calculation. So some other constants that we need. The molarity of the sodium hydroxide solution. So that was 0.1 molar. It had several zeros in it, which we don't really need to enter, but that's okay. And then we need the theoretical equivalence point. And again, that'll be in milliliters. And so based on my molarity, that theoretical equivalence point was 29.38 milliliters. So this is the one that you calculated early on. All right, that's good. So the next thing that we should do is just make sure what our titration curve data looks like. So I'm going to do a quick plot of the titration curve. So remember, that's going to be a plot of volume of base, so that's this first column, versus pH as our y variable. So I'm just going to select these two columns of data right here, click and drag to do that. And let's insert an XY scatter plot. So insert scatter plot, and let's connect the points with little line segments just so we can see what's going on. Let's move this up here. Okay, so here's our little plot. This is the pH on the y-axis and volume of base that we add. So you remember that in this titration curve, we're adding base, so the pH is going to go up. And we get to this little cliff portion right here. That's where the equivalence point is. It's the point of steepest rise. So we don't have some data in here, but we're going to guess that that point happens somewhere kind of right in here, it looks like, around 30. I mean, we predict 29.38, so that's pretty close to this point right in here. So yeah, this seems to all line up pretty well with what we were predicting. Again, my prediction and this data don't necessarily line up because I made up this molarity and so forth. It may not agree with this actual set of data that we have. Okay, so now we need to construct the Gran plot. And so if you read in the instructions, let's go back and take a look at the instruction. It says construct a Gran plot. So what is that? That's a graph of the volume of base times 10 raised to the negative pH value, that'll be our y variable, versus the volume of the base, the sodium hydroxide, that's our x-axis variable. And we want to use just the data collected between 0.9 VE and VE. And then we're going to draw a line through the linear portion of this curve and extrapolate it to the abscissa, a fancy word for the x-axis, to find the VE, because where it intersects the x-axis, that is our actual experimental equivalence volume. And then once we know that, we're going to use that experimental equivalence point volume for all our calculations after this. All right, so let's go and do that. So the first thing we need to know is what is 0.9 times VE, our equivalence point volume. So what is that? That'll be in milliliters again. I may not include all my units in all these labels, but you should do that. All right, so this we can calculate, just an equal sign with a formula, 0.9 times our theoretical equivalence point volume. There we go. And so we're going to want the data between about 26 and about 29 or 30. So let's go see if we can find that data. So here's 26.4 right there. That is our 0.9 value. So yeah, we want to take this chunk of data here going out to about 29.38. Let's see where that is. 29.35, 29.4. Why don't we just grab that bit? All right, so I'm just going to copy that. So that's a Control and a C on your keyboard. And then we're going to create a little section here where we just post that data. And so just to have some labels, this is going to be V sub B here. That's volume of my base, sodium hydroxide. And again, this is pH here. And this is just the section between 0.90% of the way to the equivalence point volume. So somewhere in here, right, to the equivalence point. So we're just using a small set of the data, but it's not the data right at the equivalence point. All right, so now we're going to do that Gran plot. And so to do that, first we need to calculate 10 raised to the negative pH power. So I'm going to put that in parentheses just so it looks a little nicer. There we go. And so we need to calculate that, so we can use a formula to do that. Equals 10 to the power, a little carry symbol there, and then in parentheses negative, and then we just click on the pH value, close our parentheses, hit enter, and then we want to copy and paste this value down the row, so just grab this little green square, click and drag, and there we go. And then finally we need to calculate the other y variable, that's going to be VB times 10 to the negative pH power. All right, so now we just calculate that. So that's equal to VB, that's this number, times our 10 to the minus pH power, that's this number. Hit enter, and we want to copy and paste that formula all the way down this column. And there we go. So this is the data that we're going to need for our Gran plot. Now let's go ahead and make the plot. So remember, this column right here is going to be your x-axis data, and this column right here is going to be your y-axis data. So to do that, I'm going to go up and insert. I'm going to insert a scatter plot, and so I'm just going to click that. All right, so it's blank because I haven't given it any data. So we need to give it data, and the way I'm going to do that is go up here to where it says Chart Design. So back from the Home menu, you'll find this menu that once you've clicked on your chart, like if I'm not on my chart, then that menu goes away. So you have to select your chart, click on it, and then there's Chart Design right here. Click on that. Then you should have a button that says Select Data. We want to click that, left click that. Now you've got some data. So let's create a data. So we want to add some new data. And it says the series name. Well, we can click on a cell to give it a name, or we can just give it a name. I'm going to call it Gran plot, like that. Then we need our x values. So we click on this little icon right here. That will let us click and drag to select our x-axis values. There they are. Then we can click on this to return to our selection screen. We do the same with the y values right here. So we click on that, click and drag to select the y values, return to the screen, and click OK. Click OK again. And lo and behold, there's our Gran plot. Now you'll want to format this a little bit better with axis labels. I haven't done that. But you see we have a graph that seems to be approximately linear. So we want to find the equation of that line. So let's go ahead and add a trend line. So up here we click on this, go down to trend line, select the over arrow right there. Let's click on more options. That'll bring up over here on the right hand side an option. Click on linear, we want that. We want to display the equation on the chart, and we want to display the r squared value as well. All right, that looks good. So we can close out of that. You might want to click on this label and just move it somewhere so that it looks pretty and you can read it easily. So somewhere up there. Now we're probably going to want to know the slope and the intercept and have them entered in cells here with a few more significant figures. But notice our r squared value, we've got 2 9s here, so that's reasonably decent. There are a few little points that wiggle off the line, but it doesn't look like the line is deviating. So in your case, your graph, you may see down here at the end that some of these points start to come off the line. If that happens, go back and delete those points because we just want the points that fall on the line. All right, so let's go ahead and calculate our slope and intercept. So our slope here, y-intercept. And so again, we know what those numbers are. We're just going to calculate them, have them in cells, because we're going to use them for other calculations here in just a bit. I like to line these up so that they're aligned along the right-hand side there. And then I'm going to just type a formula to calculate our slope. And so surprisingly enough, that formula is slope. So equal sign, S-L-O-P-E for slope, and then open a parentheses. Then it says we need our y values first. So what are our y's? These guys. So click and drag. Then a comma. Now it's clicked over here to our known x's. So we're going to click and drag to select our x values. They're now highlighted in red. And then we just want to close our parentheses and hit enter. So there's the slope. So that's the number that's up here, -8 times 10 to the -6. So we get a few more decimal points there. Do the same thing for our y-intercept. So equals intercept. You can double click this rather than typing it all in. The known y's. Yep, here are y's. Comma. Click and drag to select the x's. Close the parentheses and hit enter. Oops, enter. There we go. So there is our slope and intercept. So we need to now figure out what the x-intercept is. Go back home here. All right. So I have some weird dots here because I was entering draw mode to draw some stuff for you guys. Anyway, we're cool. We'll just go back here. Yeah, we want to figure out what our x-intercept is. Intercept? No, intercept. Let's fix that. There we go. That looks good. Better. All right, line that up. Nice. All right, so how do we figure out what our x-intercept is? So I'm going to draw some stuff for you. Go back over here, select my pen, and see if I can get this to work. Oopsie. All right, so we know the equation for a line is y equals mx plus b. And so what we want to do is find the x-intercept. So when this line crosses the x-axis, we know that y is equal to 0. And so what we basically want to do is solve this equation for x now, and that will give us the x-intercept. So subtract b from both sides, and then divide both sides by m. So we have -b divided by m will equal x. All right, excellent. So let's go back and type in a formula to calculate that. So that's going to be equal to the negative of the intercept. There's the intercept. Divided by, so / the slope. There we go, and hit enter. All right, so here is the x-intercept. So what is this according to the Gran plot? This is, I'm just going to type a little, so I type a space in here so I can type characters that Excel might think are mathematical functions. So then I'm going to use the less than sign right here, and 2 dashes. That's just kind of like an arrow pointing to this. So what is this? This is the VE experimental. And again, that's going to be in milliliters. All right, so there is our experimental equivalence point volume. So it's this number that we're going to want to use from now on. So that's going to be an important number. So let's click the good label on that. Yeah, so that one's been labeled. There's our x-intercept. All right, so let's see what the next thing is that we need to calculate. All right, compute the slope of the Gran plot and use equation 3 to find Ka. Oh, it says, by the way, compare this value, the VE that you found, with that from the phenolphthalein and the one that we estimated from the graph of pH versus VB. So we see that they're really pretty close, at least for the pH. I don't have the information about the phenolphthalein, but you'll have that in your notes. So step 2, compute the slope of the Gran plot. So we've done that, and use equation 3 to find Ka. Well, what it tells us is that the slope of the Gran plot is equal to the negative of the Ka value times gamma of HA divided by gamma of A minus. And then it reminds us that what RHA, HP they're going to call that. So that's the hydrogen phthalate acid. And when we react that with the sodium hydroxide, this proton gets taken away by the hydroxide. So we end up with just the phthalate anion here, P2 minus. So we've pulled off both protons. And what is this gamma? This gamma is a thing called an activity coefficient. If you'll go back and look at the video where I describe the Gran plot method, you'll get to learn a little bit more about these. But basically, these are correction factors for the fact that when we have ions in solution, they get stabilized by other ions. And that's going to change as the number of those ions change. And so these are numbers that vary and are going to change the stability of ions in our solution. And to keep the equilibrium constant, we had to introduce those. So these gammas, where do we get those? Well, we're going to have to calculate those in order to find Ka. So we know our slope. We know our slope equals all this. We're looking for Ka, so we're going to need to know what these gammas are. All right, so they tell us that we can calculate activity coefficients from this example. But then it says the ionic strength is changing slightly as the titration proceeds. So here at this point, sorry, let me go back to my graph. Here at this point, we are at 90% of the way to the equivalence point. And right around in here somewhere, we are at, well, it's a little bit over here, we are at the equivalence point. So as we move from here to here, the ionic strength of our solution is changing. So what is ionic strength? Well, ionic strength is just a measure of the total molarity of electric charge in our solution. So it accounts for the things that some ions, like P2 minus, carry 2 units of charge, and otherwise it depends on the concentrations of all of the ions that might be floating around in our solution. So that changes from here to here, and so we're going to use kind of an average value that's, instead of at 90% or right at 100%, is kind of halfway in between at 95%. And so that's why it says here, and it suggests that we calculate the ionic strength at 0.95 VE and use this average ionic strength to find these activity coefficients up here, right? So we have to figure out these before we can calculate Ka. And that's the big goal of this lab, is to get the value of Ka. So yeah, we're going to do that next here. Okay, so let's go back to our spreadsheet and do a couple of things. So we need to calculate 95% VE, so let's do that. 0.95 VE. And so that's easy enough to calculate. So equals 0.95 asterisk for times, and we just click on our experimental. So we're going to be using this VE from now on, not the one that we guessed up here. All right, so just click on the check mark or hit enter. So there's 95% of VE, so we're going to need that value. And another value that we're going to want to calculate is the total volume of the solution. So I'm going to have V underscore total, and again, that's going to be in milliliters. Okay, so the idea is that we started out with a certain volume of solution in the beaker that we were titrating into, right? You guys pipetted 100 milliliters of that KHP solution into that beaker and dipped your electrode in that and started titrating. When we get to 0.95 VE, we will have added 28.4748 milliliters of sodium hydroxide, right? So the total volume is just going to be the sum of those two. So this is going to be equal to our initial volume of KHP solution. So I'm going to scroll up and click on that one, right? And so we're going to add to that then this extra volume of sodium hydroxide that we've added. Those two added together make up the total volume inside our beaker when we are 95% the way to the equivalence point volume. So that's what 0.95 VE is. Equals that. So there's the volume that we have inside that beaker right now. So we're going to need that to do some calculations. So let's go back and learn how to do this by looking at this example. All right, so this example says calculating the activity coefficient. So in this example, we're going to find it at 0.95 VE in the titration of 100 milliliters of 0.02 molar potassium hydrogen phthalate with 0.1 molar sodium hydroxide. All right, so our concentrations might be a little bit different, right? And in this case, they say the equivalence point is exactly 20 milliliters, right? So we have a different equivalence point. So 0.95 VE is 19, but we've already calculated what that is for us. So it does tell us that the concentrations of H plus and OH minus are negligible compared with those of K plus, Na plus, HP minus, and P2 minus. So what does all that mean? Yeah, so remember that you guys dissolved potassium hydrogen phthalates. That's what the H and the P stand for. And so we're going to get those ions when that salt dissolves into the water. As we do the titration, we're adding sodium hydroxide. So that's where we're going to get the sodium cations from. And then as we do that titration, those hydroxide ions are going to react with the hydrogen here in the hydrogen phthalate and make water molecules. So those OHs are kind of going away. And then we're going to produce a P2 minus once we've reacted the H plus off this molecule, right? So that's just basic acid-base reaction. We're transferring a proton from the Bronsted-Lowry acid to the Bronsted-Lowry base, hydroxide in this case, to make the conjugate base, P2 minus. So P2 minus is the conjugate base of hydrogen phthalate. So this means that the concentrations of these ions are higher and much more important than the concentration of H plus and OH minus that are in the solution. So when we're going to calculate that thing called the ionic strength, which measures the total molarity of all the ions, we can ignore the H plus and the OH minus. Okay, so let's figure out how we calculate these things. The K plus, the Na plus. So here it is. In square brackets, remember that means molarity. And so what we're going to do first is we take the initial concentration, right? So what is the concentration of the KHP in that solution that you pipetted into the beaker? Well, in this little example, it's 0.02 molar. Ours is going to be a little bit different. We'll go back to the spreadsheet and find that number. And then basically what's happening is you're diluting that, right? So you're adding some extra volume to it. That's the sodium hydroxide that you've added. And so we can calculate this thing called a dilution factor. That's just a ratio of the initial volume to the total volume, right? So 119 milliliters would be the total volume of 19 milliliters of sodium hydroxide plus 100 milliliters of initial solution. So again, if we go back to our spreadsheet here, our total volume is a little bit different. It's 128. Our initial molarity is not 0.02, it's 0.02938. So, close to that, but slightly different. So we're going to use those two values when we calculate this K value. So we multiply a dilution factor times the initial concentration. That will tell us the concentration of K plus ions in our solution. How do we figure out the concentration of Na plus? It's the same kind of idea. Basically, we've diluted that sodium hydroxide. So we start off with that initial sodium hydroxide. We've only taken a small amount of that, 19 milliliters, right? That's the 0.95 VE. For us, that's different, remember? And we're going to divide that by the total volume. So again, that's a dilution factor. So we've diluted that 19 milliliters down by making a total solution that has 119 milliliters of volume. And so that gets us the 0.1. We multiply by the initial concentration by the concentration of our titrant, the sodium hydroxide, which has 0.1 molar. And that's how we'll get the concentration of sodium. So what about the concentration of HP? So I might need to say a little bit more about that. Let me just real quickly bring up a place to write some stuff down. Okay, here on my little scratch pad, this is the reaction that's going on as we're titrating. So we have the HP minus, the hydrogen phthalate, and that's reacting with the sodium hydroxide that we're dribbling in. And that's going to produce phthalate and water. Oh, and sodium cation. Let me write that over there. Okay, so how do we figure out the moles of HP at any point? Well, it will be the initial number of moles, And then every time we add a sodium hydroxide, we remove one of those moles. So I'm going to subtract off the number of moles of sodium hydroxide that we added. Similarly, how do we figure out the moles of P2 that are present at any P2 minus that are present at any point? Well, that's just going to be equal to the moles of sodium hydroxide added. So if we go back to our example, you'll see that they're kind of doing this in a clever way. So this number right here is the fraction remaining to get to the equivalence point volume. So are you 50% of the way to the equivalence point? Are you 95%? How much is left? So in this case, 0.05 means that we have 5% of the titration left. So that's the fraction remaining. So not a percentage, but a fraction. So there's 5% of the titration left. Why? Well, because we're at 95% of the equivalence point volume. So we've got 5% more, and then we're there. We're at the equivalence point. So when we are at the equivalence point, what has happened? We've added exactly enough moles of NaOH to react with all the moles that we had initially. And so there should be no moles of HP minus left over, right? Because those two would be equal. They've exactly reacted. And we will have converted all of our moles of HP minus into moles of P2 minus. So we can use that. So the fraction remaining times the dilution factor. Again, we're adding volume to this, so we need to change the dilution. And so basically, we're converting mole to mole as we move along from 0%, from 100%, 1 remaining, until 0 remaining, right? And so we can calculate what that is by just putting the fraction in, accounting for dilution, and then this is the initial concentration right here of the KHP. We can do the same thing with the P2, except instead of fraction remaining, it's the fraction completed. So we've completed 95% of the way to our equivalence point volume, so we're at 0.95. We account for this dilution factor again. We started with 100 milliliters of the KHP solution. We've now diluted it down to 119 milliliters because we've added 19 milliliters of sodium hydroxide. And then we're going to multiply by this 0.020. I just wanted to point out something that in this term, the HP minus molarity and the P2 minus molarity, we have this dilution factor times the initial concentration, and that turns out to be the same as what we calculated for K plus, right? So we can reuse that when we're doing these two calculations down here. Then how do we calculate the ionic strength? Well, we're going to use this formula. This might be a little bit confusing, but if you go back to my video, I explain this a little bit more. It's also in chapter 8, but this is how we calculate the ionic strength. So it's 1/2 times the sum of the molarity, that's what CI stands for, concentration, so the molarity of each different ion, times the charge on the ion squared. So for example, our first ion, let's say, is K plus. So we're going to have 1/2, then times the sum. That's why we're adding all of these up. So the first ion right here, this first term, has to do with K plus. And it has a molarity of 0.0168. The charge on K plus is +1, so that gets squared. Then we're going to do the sum. So we add that to the molarity of the sodium. That's 0.016. Times the charge on the sodium, that's +1. That gets squared. Plus the molarity for our HP minus, that's 0.00 whatever, times, and that should be -1 squared, but of course -1 squared is just going to be 1. Then we multiply by the molarity of our P2 minus, that's 0.0160 moles per liter, times the charge, which would be -2 squared. Of course, the negative sign goes away when you square it. So we would add all those terms up and then divide by 2, and this gives us that thing called the ionic strength. So that's the ionic strength, the total molarity of charges in our solution. And so as this changes, we're going to stabilize ions. So the higher the ionic strength, the more stable our ions are in solution, and the more those activity coefficients are going to become important, the more they're going to differ from 1, a value of 1. Okay, so good. Let's do that now in our spreadsheet. Okay, so we're going to try to do all this stuff in our spreadsheet. So let's go back to our spreadsheet. right here. There we go. Okay, so we want to calculate the K plus concentration, the molarity of K plus. Right, so that'll be in units of molarity. Okay, so again, that is equal to that dilution factor. And so that's going to be the volume of KHP that we have. So that's way up here, right? The volume of KHP solution, 100. Divided by the total volume. We calculated what that total volume is here. And then we multiply that times the initial concentration of our KHP solution. And so we have the molarity of our KHP solution up here. So I can click on that. And that should be everything. So hit enter. There we go. There's the molarity of our K plus. Now we need to do the molarity of our sodium in A plus in the same way. Again, units of molarity. And we want to calculate that by the dilution factor. So in this case, we need the volume of sodium hydroxide that we've added. So what is that volume? That's this volume right here to get us 95% of the way to the equivalence point. And then again, we're going to divide by the total volume and then multiply that by the molarity of our sodium hydroxide solution. And so that's up here. That's that number. Enter. All right, so there's the molarity of our Na+. All right, so then we need to calculate the concentration of our HP minus, again in units of molarity. And so again, that's going to be the fraction remaining. So what fraction remains of this titration to get us to the equivalence point? We can actually calculate that using our volumes. So we have added this volume, right? Yeah, fraction of the way to that. So that's going to be 1 minus how much is left. So we've done this volume divided by the equivalence point volume, which was where? Right up here. Yeah, that's it. So that number is also going to be equal to 0.05. So you could just type in 0.05, but later we may have volumes that aren't quite easy to write down a decimal form for, so we can calculate them from this ratio, okay? So 1 minus the volume added divided by the equivalence point volume will give you the fraction left. And then we multiply that by, if you remember, go back to our thing here, this dilution factor and this initial concentration. But that's just the same as the K plus concentration. So I'm going to make use of that fact and just multiply by our K plus concentration. So we hit enter, and there we go. Now we need the molarity of our P2 minus. I'm just going to write it like that without the exponent, but that's okay. You guys know what that is. All right, so we will molarity units there. And so now we need to calculate this. So now this is the fraction completed. And so we have added 28.47 milliliters of a total 29 to get us to the equivalence point volume. So there's the fraction complete. That'll be 0.95 times, again, this K plus number right here. Okay, so you see we have very little HP minus left in the solution, right? So we've already reacted 95% of it. So there's very little of it left. Most of it has been converted to P2 minus already. All right, so those are those concentrations. Now we're ready to calculate ionic strength. So I'm going to use the capital letter I for ionic strength rather than that Greek letter mu, which our book uses, just because I don't want to have to type in a Greek letter into Excel. We could use the lowercase u letter, but sometimes we've used that before for uncertainty. So just so it doesn't get confusing, I'm going to use capital I for ionic strength. All right, there we go. And that has units of molarity. All right, so what is that? That is equal to 1/2. 1/2 is 0.5 times, and then in parentheses, we've got to have all of these ions. So first I need the concentration of the ion, and then times its charge, plus 1 in this case, squared. Then we need to add to that the next ion, so that'll be the sodium concentration, times, again, the charge, which is plus 1 squared, so carry 2, plus the next ion, which is my HP minus, so that, times the charge, which is negative 1, that gets squared, and then plus our last ion, which has this molarity, times its charge, negative 2, that quantity squared. Then we can close the parentheses on our sum here, and it gets multiplied by 1/2, right? So we had that parentheses. We've closed it here. So hit enter, and that should be our ionic strength, 0.665 molar. Okay, so now we are ready to use this ionic strength to determine what those gammas are, those activity coefficients. So we're going to need to go back to our example and take a look at that. Okay, so how do we estimate these activity coefficients? So it says we have to interpolate a table. So what table is this that they're talking about? Well, it's the table in your book. So in chapter 8, on page 165, there's this table 8-1. And so it lists for us activity coefficients at different ionic strengths. So these are the ionic strengths, mu, in units of molarity. So there's 0.001 molar, 0.005 molar, 0.01 molar, and so on. And then it lists ions that have charges of plus or minus 1. Here are a whole bunch of ions. Here's some ions with charge plus or minus 2. So here are a whole bunch of ions, plus or minus 3, and so on. So if we knew the ionic strength and we knew which ion we were talking about, we could look it up. So if we go back to our table, it says, in this table we find that the hydrated radius of phthalate, this ion right here, is 600 picometers. And then it tells us that the size of HP is not listed, but we will suppose that you've just stuck one little puny hydrogen on there so that its hydrated radius alpha is also going to be 600 picometers. So what a hydrated radius is, if you watch that other video, you might remember this, but it's the radius of this ion plus any water molecules that are closely associated with that. So basically, we're going to use this 600 row right here, and so we're going to be reading across there. So what you'll notice is that the ionic strength that we calculated is 0.06. So we go back to our table. There's no 0.06 here. There's 0.05, there's 0.01, and there's 0.1. So 0.06 is not on our table, so that sucks. But we know that 0.06 is going to be between 0.05 and 0.1. So we could do something called interpolation. So for example, if we were like halfway in between 0.05 and 0.1, so that would be 0.075. So if we were exactly halfway between, we know that the activity coefficient is not going to be 0.835 like it would be for 0.05, and it's probably not going to be 0.8 like it would be if we were at an ionic strength of 0.1. It's probably going to be in between. So where? Well, probably halfway in between, because we are halfway in between 0.05 and 0.1. So we are not quite there. Ours is a little bit different. We're at 0.06, which is not halfway. So how would we figure out what the corresponding place is that's kind of in between here, but not quite halfway? You know, we're only a fraction of the way. So not 50% of the way, but maybe 26% of the way, or whatever it happens to be. How do we do that? Well, to do that, we need to use a technique called linear interpolation. So let me tell you about that. I'm going to go to my little chalkboard here. So here's our data table right here. And we want to look at, this row right here. Let me change color. This row right here. And we're trying to interpolate between these last two values. So we want to figure out what would be the activity coefficient that's right in between here. So the way we can think about doing that, I drew a little axis here that shows 2 points. So we're going to imagine that you can connect a straight line between those 2 points. We know what the y value is at this point x1. So let's say that x for us is going to be the ionic strength, right? So we know what the value is at x1, so it's this 0.05 right here, so that would be the 0.835. We know what it is at x2, it's the 0.8. We also know what the, sorry, these are the ionic strengths, so this would be 0.05, this would be 0.1. The y values would be the gamma values. So our y's up here, they're going to be our gamma values. All right, so we actually know what our ionic strength is. Our ionic strength is sort of in between here. It's at 0.067. So kind of squeeze it in there. So we know what that x value is. And so a good way to estimate it is kind of go up here and say, oh, it's going to be the corresponding y value. That's right here. And we don't know what that is. That's what we're trying to figure out. So the way we can figure that out is to write kind of a ratio. So we're going to say that this y value that we don't know, that it is different from the value that's below it, this y1 here. And if we were to divide by the difference between the known y values, the thing that I'm calling delta y, right, that delta y, that should be the same as the proportion change of the x to the delta x. So the x value right here that we know, this x value, minus x1 divided by the delta x. So that would be the difference between these x1s and x2s. So delta x would just be x2 minus x1. Delta y would just be y2 minus y1. All right, so what I want to do is solve this equation now for y, and that would let me linearly interpolate this. So if my x was exactly halfway in between, we know it would be halfway in between these two numbers. So let's just solve this for, we're going to multiply both sides by delta y. So we have y minus y1 is equal to x minus x1 times delta y divided by delta x. Okay, so I just multiplied both sides by delta y. I need to get y by itself, so I'm going to add plus y1 to both sides. So I have y is equal to y1 plus x minus x1 times delta y over delta x. And remember, our y's are the gamma values, and our x's are the ionic strengths. So in this table, if we were plugging numbers in, my y1, that's going to be the lower of my y values, so that's going to be 0.835 plus our x value, that's the 0.067 ionic strength, minus the ionic strength, that's the lower one, that's the 0.05, times delta y, so that's the difference in y2 minus y1, so that's going to be 0.8, that's our y2 gamma coefficient, minus 0.835. So that would be our y2 that's associated with x2 and our y1 associated with x1. And so our delta x is just going to be the difference in x2, which is 0.1, minus 0.05. All right, so that's the way we would interpolate our y value. So we're going to go back to Excel and basically enter this formula into Excel. So it might be helpful for you to write this down somewhere. I'll have it on my screen, but you might want to write this down somewhere so that you can enter this formula into Excel and we can make sure that we're clicking on all the right numbers. Okay, so let's go back to Excel. All right, so I'm going to give this a little heading. And so we're going to call this I2. That's the higher of the two ionic strengths. And so that was going to be 0.1. And then we've got I. Maybe I'll use subscripts or something. You know, why don't I do that? Let me just clean this up real quick. I underscore 2 units of molarity. Sorry, I get a little hung up over some of those things sometimes. All right, and right justify. There we go. All right, we're going to call this one I underscore 1. Again, units of molarity. colon, enter. And what is that ionic strength going to be? That's going to be 0.05 from our table. And then we need our I'm going to call this x just so we're remembering that this is the unknown value that we just figured out. And so we know what that is. I'm just going to go ahead and put it in here for completeness, but it's the ionic strength that we just calculated. So I'm just say equal, it's this thing. Okay, yes, we already had calculated that, but I've entered it again here just so it's there for completeness. And then here I'm going to calculate delta x. All right, and so what is that? That is x2 minus x1. Enter. So we got that. All right, so now we need to do the same thing for our gammas. And so we're going to have gamma underscore 2, gamma underscore 1. And our gammas, they are unitless quantities, so they don't have any units associated with them. And then finally, we're going to have our gamma underscore y. This is the thing that we're trying to find, okay? So I gave myself a little bit of space in here because I'm going to have two little column labels. So we're going to have HP minus, and over here we're going to have P2 minus, because we got to calculate activity coefficients for both of those. So we need to get what those activity coefficients are. So for the HP, it's going to be 0.8 and 0.835. And this is where we're going to do our calculation. Let's just go back and check that in the table, right? So if this is x2, this is x1, then that makes this right here y1, and that makes this y2. So y2 is 0.8, y1 is 0.835. There we go. So y2 is 0.8, 0.835. Good. You know what? I'm going to go down here and delete that because I'm going to do something else here in a second. Let's do the same thing for our P2s. Let's go back to the table. All right, so now we've got a -2 charge, and we're going to be using that 600 value. And so we've got, for the higher ionic strength, 0.1, we've got a value of 0.405 and 0.485. So we got 0.405 and 0.485. There we go. And then right here, I'm going to calculate delta y. And so that's just going to be equal to y2 minus y1. Enter. And we can just copy and paste that formula over to the right-hand side here. Good. And so we got those two differences. And now we're ready to have our gamma underscore y colon. And so this is the thing where we want to type in our linear interpolation formula. All right, so if you have that formula handy, we're going to type that in. All right, so equals y1. So what is y1? Y is our gammas, so y1 is this number. Then we're going to say plus, and then the quantity, so we want to open up our parentheses, x minus x1. So what is x? This is x right up here, minus x1. What is x1? Our ionic strength, so that's this number. Then you can close your parentheses, and then we're going to multiply that, so they're asterisk. We're going to multiply that by delta y, so here's delta y, and we're going to divide that by delta x, so here's delta x. So that's our formula. We hit enter. Okay, so let's check this out. It's always good to do a reasonability check. So we get a value of 0.82. So lo and behold, that is in between 0.8 and 0.835. If you get a number that is not in between 0.8 and 0.835, you have done something other than linear interpolation. So go and check your formula because there's an error in it. All right, so, and we know that we're at an ionic strength of 0.06, so that's a little bit closer to the ionic strength of 0.05. So we might expect this to be a little closer to the 0.835 value than the 0.8, and it is. Okay, so now since we've entered our values here in this right-hand column, we can just click and drag this formula over here. Uh-oh, it didn't like something. Oh, I know what it did, because up here we didn't have, You see, when you copy and paste formulas, sometimes things go awry. So we need to lock down our cell references up here in this bit. or you can just copy and paste them over here as well. But we'll just lock them down. So I'm going to go back to this formula right here. You click on that. So all the references that are up here, we need to make those fixed cell references. All right, so this value right here, that needs to be a $L, $49. We need a $L, $48, and a $L, $50. All right, so for that formula, we lock down those 3 cell references so that when I copy and paste, they won't change. So click the check mark right here to accept those changes that you made into the formula up here in the formula bar. Boom. All right, we got the same number. Now we should be able to click and drag. Woohoo! So 0.458 is indeed between 0.405 and 0.485. So interestingly, it doesn't help those of us with a little bit of dyslexia permuting those numbers, but that's okay. All right, so those are the gamma values. Yay! Whew. Why did we go to all this work? What's going on? What's our point? Yes, our goal is to calculate the acid dissociation constant for this acid. So this was measuring that Ka value. So in order to do that, right, we know what? We know that slope is equal to the negative of all this stuff. So let's go back to our chalkboard here and just write that down. We'll do some math. Scroll all that other stuff out of the way. So remember, slope from our Gran plot is equal to negative Ka times the activity coefficient associated with the hydrogen phthalate divided by the activity coefficient associated with the phthalate. All right, so what we want to do is solve this equation for Ka. So we multiply both sides by gamma P2 minus, so slope. I'm also going to multiply both sides by the -1 here. So minus slope times gamma P2 minus, and then I would divide both sides by gamma HP minus, and that's going to be equal to our Ka value. Good, so write that down. We want to enter that formula into Excel. So back to Excel we go, and here we are ready to calculate our Ka value. Remember, Ka's equilibrium constants are unitless, so we don't need to type a unit for that. Okay, so what is that equal to? Again, that's equal to the negative of the slope. What's the slope? It's up here, so this number, negative of that, times what? Times the gamma for the, back to our board here, gamma for the P2 minus. All right, so gamma for the P2 minus, here's our P2 minus column, it's that number. And we're going to divide by the gamma for the HP minus, that's that number right there. So we're going to hit enter, boom. Go back to the instructions, see what do we do next. So yay, there's the equilibrium constant, 4.69 times 10 to the minus 6. This is a weak acid, right? So we've got a Ka that's less than 1. No surprises there. Sorry, that's scrolling around too much, making you dizzy. Find the Ka. There we go. We've found the Ka. Okay, there we go. Moving on to part 3. From the measured slope of the Gran plot, we just did that, and the values that we just calculated for gamma HP minus and gamma P2 minus, calculate pKa. All right, so we have calculated pKa. I'm sorry, we've calculated Ka. Let's calculate pKa now, pKa. All right, so how do we do that? What is pKa? Back to my little whiteboard here just to remind you that P of anything is the negative log of that thing, right? So pKa is going to be the negative log of our Ka value. All right, so let's just do that in Excel. So go back to Excel. Hello, Excel. So pKa equals the negative, so negative sign, log, L-O-G, open parentheses because it's a function, and we're just going to input our Ka value. So just click on that, close the parentheses, and hit enter. So there's our pKa value. So if we go back to the instructions, there's some other stuff that it asks you to do. So it says, then choose an experimental point near 1/3 VE and whatever, and then we have to use equation 1 to find pKa, and we have to go back and recalculate all of these things again at each of those 2 points, and then we would average those values. So we're not going to do that. Aren't you glad? Yes, you are. So we're going to stop our calculation here. You will have 2 values to average, however, because remember, this is just one set of data. You guys, your group, did 2 titrations. So you're going to repeat this for your second titration, and then you're going to calculate the average pKa value. The last thing, though, that I would like you to do, it says compare the average value from your experiment with pK2 from phthalic acid listed in the appendix of the textbook. So you should do that. So where is that appendix? Let's go back. Okay, so in the back appendix of your book, you can look up Kas of weak acids. They're listed alphabetically, so you'll have to look underneath the Ps. It gives the structure of the full acid. This is a diprotic acid, and it highlights the acidic protons for you. This column right here lists the pKa values. So this is the pKa value for the first proton that you remove. This is the pKa value for the second proton. These are the Ka values, and these are the pKa values at a different ionic strength. So because we've used activity coefficients in calculating our Ka here, we've sort of extrapolated back to this value. So we're comparing to 5.408 as our pKa. Let's go back to our spreadsheet. That's not spreadsheet. Hello, spreadsheet. And we got 5.32. So that's slightly different than 5.4, but not terribly. And again, I don't really know that my concentrations and so forth here match with this data set exactly. So that might explain part of the deviation. But we're certainly in the ballpark. So I think we've done a very respectable job of calculating that pKa. All right, so just repeat this calculation for a second run, and you should be good to go. I will save this spreadsheet as well so that you can go back and look at this spreadsheet if you need to check out any of my formulas or remember anything that I've done. So I know these calculations are a bear, but bear with it and you'll be fine. So you can do this. You got this. Yes, do your calculations. Feel good about, pat yourself on the back because this is hard work with Excel. So you're learning a lot about Excel. These are great skills to transfer to other things that you might do in the STEM fields. So have a good evening, afternoon, day, whatever it happens to be for you.